So it tells us that within a black hole, a whole new space-time can open up in the future history of this universe.
The general idea is that our universe came into existence some 13.8 billion years ago, and that it all started with the Big Bang. Eventually, the universe began expanding. Galaxies were formed, stars were born, and planets came into existence. In one of those galaxies, the Milky Way, life came into existence. This life has now evolved to the point where it began to wonder about the origins of life and its place in the universe. What if everything we know about the universe is wrong? What if the Big Bang isn't the beginning of the universe? And what if what we see inside our cosmos is nothing other than the result of being inside a black hole that came into existence from some parent universe? This unconventional theory suggests that if black holes that form in our universe give birth to baby universes, our cosmos might be nothing other than the product of another black hole. But what is the reasoning behind this claim? What does it mean if we live inside a black hole? Join us as we dig into details of the latest theory that the Big Bang could be wrong and we might have been living inside a black hole all this time. Let's rewind the clock. Before humans existed, before Earth formed, before the sun ignited, before galaxies arose, before light could even shine, there was the Big Bang. This happened 13.8 billion years ago. But what about before that? Many physicists say there is no before that. Time began ticking, they insist, at the instant of the Big Bang. And pondering anything earlier isn't in the realm of science. We'll never understand what pre-Big Bang reality was like, or what it was formed of, or why it exploded to create our universe. Such notions are beyond human understanding. But a few unconventional scientists disagree. These physicists theorize that a moment before the Big Bang, all the mass and energy of the nascent universe was compacted into an incredibly dense yet finite speck. Let's call it the seed of a new universe. This seed is thought to have been almost unimaginably tiny, possibly trillions of times smaller than any particle humans have ever been able to observe. And yet, it's a particle that can spark the production of every other particle, not to mention every galaxy, solar system, planet, and person. If you really want to call something the God particle, this seems an ideal fit. So how is such a seed created? One idea, bandied about for several years, notably by Nikodem Poplawski of the University of New Haven, is that the seed of our universe was forged in the ultimate kiln, likely the most extreme environment in all of nature, inside a black hole. It's important to know, before we go further, that over the last couple of decades, many theoretical physicists have come to believe that our universe is not the only one. Instead, we may be part of the multiverse, an immense array of separate universes, each its own shining orb in the true night sky. That led to another related idea made famous by Stephen Hawking, that each time we create a black hole in our universe, it could give rise to a baby universe that's only accessible to an observer that crosses inside that black hole's event horizon. Could our universe then actually have been spawned by a black hole that was created in some sort of grandparent universe? And do we give birth to a new universe each time a new black hole is created? But what is the reasoning behind these theories? Well, it's actually fascinating. The defining feature of a black hole is the existence of an event horizon, a boundary that tells a very different story for an object outside of it versus one inside of it. Outside of a black hole's event horizon, any object will experience its gravitational effects, as the space will be curved by the black hole's presence. but it can still escape. If it moves fast enough or accelerates quickly enough in the proper direction, it won't necessarily fall into the black hole, but it could break free of the black hole's gravitational influence. Once an object crosses over to the other side of the event horizon, however, it's immediately doomed to be subsumed into the black hole's central singularity. Because the fabric of space-time is severely curved inside a black hole, an infalling object will reach the singularity within seconds of crossing the event horizon, growing the black hole's mass in the process. To someone located outside the event horizon, the black hole appears to form, gain mass, and grow over time. What does this have to do with our universe, though? If you were to take all of the known, measurable forms of matter and radiation in the observable universe, you'd have to add up all of the following: normal matter, made from protons, neutrons, and electrons; neutrinos, ghostly fundamental particles that rarely interact with normal matter; dark matter, which dominates the universe's mass but has so far eluded direct detection efforts; photons, or particles of light, which carry energy from every electromagnetic event throughout cosmic history; and gravitational waves, which are created every time a mass moves and accelerates through the curved fabric of space-time. At the farthest limits of what our instruments can possibly detect, we can see up to about 46 billion light-years away in all directions. If you add up all the energy from all of these forms throughout the entire observable universe, you can arrive at an equivalent mass for the universe using Einstein's most famous relation, E equals mc squared. Then, if you like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is the same as it would be if you compressed any large enough collection of mass or energy into a single point. It would form a black hole. What's remarkable about Einstein's theory of gravity is that if this collection of mass and/or energy isn't charged electrically and isn't rotating or spinning, without angular momentum, the total amount of mass is the only factor that determines how large the black hole is, what astrophysicists call a Schwarzschild radius. Remarkably, the Schwarzschild radius of a black hole with the mass of all the matter in the observable universe is almost exactly equal to the observable size of the visible universe. That realization on its own seems like a remarkable coincidence, raising the question of whether our universe might actually somehow be the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. In the mid-1960s, a discovery revolutionized our concept of the universe. A uniform, omnidirectional bath of low-energy radiation appeared from all locations in the sky. This radiation had the same temperature in all directions, now determined to be 2.725 Kelvin, just a few degrees above absolute zero. The radiation had a particularly perfect black body spectrum, as though it had a hot, thermal origin, and appeared identical to within 1 part in 30,000, no matter where you looked in the sky. This radiation, originally called the primeval fireball and now known as the cosmic microwave background, represented critical evidence that our universe is expanding and cooling because it was hotter and denser in the past. The farther back we extrapolate, the smaller, more uniform, and more compact things were. Going all the way back, this picture of the hot Big Bang appears to approach a singularity, the same condition found at the central interiors of black holes, a location where densities, temperatures, and energies are so extreme that the laws of physics themselves break down. Something remarkable happens when you look at the equations that govern a black hole as well. If you start just outside the event horizon and escape to an infinite distance away from the black hole, you'll find that your distance, r, goes from r, the Schwarzschild radius, to infinity. On the other hand, if you start just inside the event horizon and track your distance from the black hole to the central singularity, you'll find that same distance, r, instead goes from r, the Schwarzschild radius, to 0. Big deal, right? No, it actually is a big deal. For the following reason: if you examine all the properties of space outside of a black hole's event horizon from r to infinity, and compare them to all the properties of space inside the black hole's event horizon from r to 0, they are identical at every single point. All you have to do is replace the distance, r, with its reciprocal, 1 over r, or more accurately, to replace all instances of r over r with r over r. And you'll find that the black hole's interior is mathematically identical to the black hole's exterior. It's almost like taking a spherical orb that's 100% reflective, a perfect mirror, and noticing that the entirety of the universe that's located outside of that sphere is now contained, albeit distorted, in the mirror image that's reflected on the sphere's surface. As our understanding of the universe has improved and been refined over the past few decades, 2 new discoveries have rocked the foundations of cosmology. The first was cosmic inflation. Instead of arising from a singularity, it now appears that the universe was set up by a rapid, relentless state of constant, exponential expansion that preceded the hot Big Bang. It's as though there were some sort of field that provided an energy inherent to space itself, causing the universe to inflate, and only when inflation ended did the hot Big Bang begin. The second was dark energy. As the universe expands and becomes less dense, distant galaxies start to recede from us at an accelerating rate. Once again, albeit with a much smaller magnitude, the universe behaves as though there's some sort of energy inherent to space itself, refusing to dilute even as the expansion of space continues. People have speculated that there might be a connection for as long as inflation and dark energy have both been around. The fact that there's a fundamental difference between the expansion rate of the universe that you infer depending on which of the 2 classes of methods you use to measure it only strengthens that conjecture. One potential explanation that stubbornly persists for reconciling this discrepancy is that there was a stronger form of dark energy early on, one that existed after the end of inflation but decayed away before the cosmic microwave background scattered off of the primeval plasma for the final time. Perhaps inflation and dark energy have more in common than we realize, and perhaps black holes will provide a critical insight into the nature of that link. What might that connection be? Once again, black holes could be the answer. Black holes gain mass as material falls into them and decay, losing mass via Hawking radiation. As the size of the event horizon changes, is it possible that this changes the energy inherent to the fabric of space to an observer located inside the event horizon? Is it possible that what we perceive as cosmic inflation marks the creation of our universe from an ultra-massive black hole? Is it possible that dark energy is somehow connected to black holes as well? And does this mean that as astrophysical black holes have formed within our universe, that each one gives rise to its own baby universe somewhere inside of it? These speculations have been around for many decades, and although we lack a definitive or provable conclusion, there are certainly some mathematically compelling pieces of evidence that suggest a link. Nevertheless, many models and ideas abound, and this line of thought continues to be compelling to many who research black holes, thermodynamics, and entropy, general relativity, as well as the beginning and end of the universe. Unfortunately, every physical model put forth, at least so far, has failed to make unique predictions that can do the following 3 things. 1. Reproduce all the successes, like the already observed phenomenon that the inflationary hot Big Bang has already successfully accounted for. 2. Explain and/or account for observed phenomena that the prevailing theory cannot. 3. Make new predictions that differ from those predicted by the current leading model that we can then go out and test. Perhaps the most famous attempt at this is Roger Penrose's conformal cyclic cosmology, or CCC, which does make a unique prediction that differs from the standard cosmological models: the existence of Hawking points, or circles of unusually low temperature variance in the cosmic microwave background. Unfortunately, these features do not robustly appear in the data, relegating the idea that our universe was birthed from a black hole and the idea that black holes give rise to baby universes back to one that's purely speculative. There's a lot to like about the idea, and there's a connection between black holes and the birth of universes from both physical and mathematical points of view. It's plausible that there's a connection between the birth of our universe and the creation of an extremely massive black hole from a universe that existed before our own. It's plausible that every black hole that's been created in our universe has given rise to a new universe within it. Unfortunately, what's missing is the key step of a uniquely identifiable signature that could tell us whether this is the case or not. That's one of the most difficult steps for any theoretical physicist, to determine the imprint of a new idea on our observable universe, distinguishing that new idea from our old, prevailing ones. Until we successfully take that step, work will likely continue on these ideas, but they will only remain speculative hypotheses. We don't know whether our universe was birthed by the creation of a black hole, but at this point, it's a tantalizing possibility that we would be foolish to rule out.
One of the basic rules of the universe is that nothing is perfect. Perfection simply doesn't exist. Without imperfection, neither you nor I would exist. Stephen Hawking. Stephen Hawking, a scientific genius, revolutionized our understanding of the universe through his profound contributions to cosmology. Despite battling ALS, his work and enduring legacy continue to inspire and shape scientific exploration. Hawking's groundbreaking discoveries, typically his work on black holes, pushed the boundaries of knowledge and challenged established theories. Stephen Hawking's black hole theory has been debated by scientists for years, but we may finally have proof that it exists, thanks to the James Webb Space Telescope, or JWST. Known as one of humanity's most advanced astronomical tools, the Webb Telescope, through its unparalleled capabilities, has enabled the discovery of a wide variety of black holes, ranging from faint, distant ones to a few that are exceptionally bright and lie even farther away. This data is about to alter our perception and understanding of these enigmatic celestial bodies. Join us as we dig deep into how James Webb could change everything we know about black holes. Black holes can often be misunderstood or mistaken for something evil. What are they, actually? Well, they're interestingly fascinating objects in space, places where matter has been crunched down into an intensely compact area. If Earth was, hypothetically, crushed into a black hole, it would be under an inch across, yet the object would still be extremely massive, as it would contain the entirety of our planet's mass. The result? A place with a gravitational pull so strong, not even light can escape. This can make black holes seem like omnipotent, terrifying objects, with an insatiable diet for stars and planets. And in the mind of the public, black holes are often imagined as huge cosmic vacuum cleaners that suck up everything in their path. This is an evocative but incorrect idea. A black hole is not, and does not create a vacuum, but quite the opposite. It attracts through the effect of gravity, because the density of its mass is so enormous. It follows that we should have nothing to fear if the sun were to be replaced by a black hole of the same mass. Though our world would be much colder and darker, the planets would continue to orbit undisturbed because the mass of the black hole would be equivalent to that of the sun. The existence of black holes stems from the theory of general relativity published by Albert Einstein in 1915, and the subsequent work of Robert Oppenheimer, Karl Schwarzschild, Subramanian, Chandrasekhar, and others. Space and time form a fabric that is curved by mass like a trampoline. A black hole is a ball so heavy that it has at its center a singularity, a region so infinitely dense that it collapses the bottomless trampoline. Any object we place nearby will tend to fall towards the ball, so the gravitational effect of the black hole is felt in its surroundings. Astrophysicists have been able to identify many such black holes by discovering cosmic objects orbiting around an apparent nothingness. This gravitational pull reveals the presence of something that is otherwise completely invisible. These black holes are often called stellar black holes. They originate after the death of a star whose internal gas pressure pushing outwards can no longer counteract the enormous force of gravity, which compresses its remaining matter until it collapses into a black hole a couple of dozen times the mass of the Sun. These are tiny compared to those that can store up to millions of solar masses, the supermassive ones that sit at the center of many galaxies. At the other extreme, there are black holes even tinier than the stellar ones, micro-black holes formed in the early universe. Regardless of their size, they are all surrounded by an invisible boundary called the event horizon, the point of no return beyond which nothing can escape, not even light. Around that horizon, the masses of dust and gas are so accelerated by the gigantic influx of gravity that they heat up and glow, emitting a radiation and sometimes forming an accretion disk, which allows us to observe the shadow that the black hole itself casts on the luminous ring. Thanks to this effect, the Event Horizon Telescope, or EHT, an international collaboration of ground-based radio telescopes, succeeded on April the 10th of 2019 in providing humanity with the first image of a black hole, which occupies the center of galaxy M87. In 1974, a study by Hawking published in Nature shook the science of the time by proposing that black holes were not so black, nor did they grow endlessly as physicists, including himself, had previously assumed. His genius was to combine two traditionally irreconcilable worlds: general relativity, the Einsteinian gravity used to explain the formation and evolution of black holes, and quantum mechanics, which describes the nature of the subatomic world. In his earlier papers, Stephen Hawking had shown how relativity led to the singularity of a black hole, but then it was necessary to crack open the quantum chest to explain what was going on there. As Hawking would explain in the public version of his theory, formally incorrect for the sake of easier comprehension, as physicist Ethan Siegel explained, quantum theory suggests the continuous creation of virtual particle-antiparticle pairs that annihilate each other almost instantly. But if this happens right at the edge of a black hole's event horizon, it may result in the negatively energetic antiparticle falling inwards, stealing energy from the black hole, and its partner escaping into space with identical positive energy. Eventually, this would lead to the total evaporation of the black hole, with no matter or energy escaping from it. Although, as Hawking pointed out in his study, for a black hole of solar mass, this is much longer than the age of the universe. In much smaller black holes, it would be faster, culminating in a final explosion equivalent to 1,000,000 1-M-ton hydrogen bombs, he wrote. Hawking's demonstration that black holes can emit radiation is his most important result. Juan Malsudina, a physicist at Princeton's Institute for Advanced Study, who has made major contributions in string theory and quantum gravity, says. But at the time, this Hawking radiation opened a real schism between relativistic and quantum physicists, as the latter now had a radical problem. If, according to quantum physics, the information associated with particles is never destroyed, but no matter or energy ever escapes a black hole, how can a black hole simply disappear, taking this information out of existence. Hawking radiation is widely accepted in current physics, although it is almost impossible to measure and therefore verify. Paradoxically, it is expelled in greater quantities by smaller, undetectable black holes, while the larger ones, those that astrophysicists can study directly, produce so little that it is indistinguishable from the cosmic background radiation. But at least a similar phenomenon has been recreated in the laboratory. Researchers at the Israel Technion Institute of Technology have generated analogs of tiny black holes that work with sound rather than light, and have managed to demonstrate something similar to Hawking radiation. These experiments have confirmed two of the physicists' predictions: that the radiation is spontaneous, it is generated from empty space, and that it is stationary, it does not change in intensity over time. But for its part, the so-called information paradox has remained the most important of the questions raised by Hawking's work, in the opinion of Maldacena. The question has kept physicists busy for the last half-century, including Hawking himself, who, until his death, searched tirelessly for a theory capable of unifying general relativity and quantum mechanics. In other words, a quantum theory of gravity that describes what happens inside black holes. The famous physicist's last words proposed a solution to information retrieval. In the 1970s, John Wheeler, who popularized the term black hole, and Jacob Bekenstein claimed that black holes have no hair, in the sense that the only properties a black hole could have were its mass, its electric charge, and its angular momentum. Cambridge University physicist Malcolm Perry, a collaborator of Hawking, says, "Thus, if one observed a black hole, you could tell nothing about how it was formed, since all other information is lost inside it. The event horizon is, so to speak, a denuded boundary shorn of all information." However, in 2018, Hawking, Perry, and their collaborators found a theoretical way to propose that black holes can have soft hair, if you will, an infinite collection of extra properties that a black hole can have, says Perry. As Marika Taylor, a physicist at the University of Southampton, whose PhD thesis was supervised by Hawking, says, this metaphorical hair suggests ways in which black holes may keep track of information at their surfaces, so that this information is ultimately recovered. But Perry cautions that while these ideas advance a possible resolution of the information paradox, they are not the final word. My view is that soft hair is part of the resolution of these puzzles, but not all of it. There is further to go, he says. Recently, other models in addition to soft hair have emerged. There have been exciting developments about recovering information from black holes over the last year or two, adds Taylor. For Maldacena, these new developments represent important milestones in the analysis of the information paradox, he says. According to Tom Banks, a Rutgers University physicist who shared scientific discussions with Hawking, the Britain's contributions have been made the most important single piece of work contributing to our understanding, still very limited, of the connection between quantum mechanics and general relativity, he says. This is a road that has been traveled for half a century and where much remains to be done. Progress is good, but the timescale for solving these deepest of all problems is long. Andrew Strominger, co-author of the Soft Hair Study at Harvard University, says, "We have been trying to understand black holes for 100 years. I hope we can wrap it up in another 50, he says. Responding to the expectations of the scientific community, a recent revelation from the James Webb Space Telescope, one of humanity's most advanced astronomical tools, has left scientists astounded as shedding light on the mysterious nature of black holes. Previously, the existence of black holes in the cosmos had always been an area of extensive study, yet JWST's revelations have exceeded astronomers' wildest dreams. The JWST, through its unparalleled capabilities, has enabled the discovery of a wide variety of black holes, ranging from faint, distant ones to a few that are exceptionally bright and lie even farther away. This data is about to alter our perception and understanding of these enigmatic celestial bodies. Many of the newly discovered black holes lie at redshifts between 4 and 6, corresponding to a universe aged around 1 to 1.5 billion years. The JWST's discoveries at these intermediate redshifts are about tenfold more than the astronomers' initial estimates, prompting further study and introspection into these results. The JWST's detailed observations have also unveiled some of the most remote black holes ever identified. One confirmed discovery lies at the heart of a well-studied galaxy, GNZ11, exhibiting a redshift of 10.6. This suggests that the seeds for black holes had already manifested and started to form supermassive entities, astonishingly early, about 400 million years post the Big Bang. In fact, the existence of cosmic titans, which have masses millions and even billions of times that of the Sun, doesn't constitute a problem when supermassive black holes are seen in the local universe. However, supermassive black holes become an issue when they are seen in the early universe, and they already have masses equivalent to billions of suns. That is because there must be some mechanism that allows supermassive black holes to rapidly gather mass and grow in such giant sizes, yet all the existing mechanisms for this growth suggest this process proceeds too slowly for objects like this to exist just after the Big Bang started. Royal Society Universe Research Fellow at Maynooth University, John Reagan, describes the problem with a somewhat disturbing analogy. It's like seeing a family walking down the street and they had 2 6-foot teenagers, but they also have with them a 6-foot-tall toddler. That's a bit of a problem. How did the toddler get so tall? And it's the same for supermassive black holes in the universe. How did they get so massive so quickly? This issue was further complicated when the James Webb Space Telescope discovered the most distant and earliest supermassive black hole. Located at the heart of the galaxy Sears 1019, this black hole has a mass of 9 million times that of the Sun, which makes it relatively diminutive for a supermassive black hole. Yet, even at this size, the existence of this just 570 million years after the Big Bang is challenging to theories of black hole growth. And this 9 million solar mass black hole wasn't alone. The same observing campaign that revealed this supermassive black hole, the Cosmic Evolution Early Release Science, or SEERS survey, also uncovered 2 other supermassive black holes that existed both 1 billion and 1.1 billion years after the Big Bang. According to Canadian University of Western Ontario professor Shantanu Basu, with each new discovery, the constraints on our existing ideas become stronger. We were worried when supermassive black holes were seen 800 million years after the Big Bang. SEERS just increases the challenge tremendously, Basu says. This suggests that supermassive black holes are common in the relative infancy of the universe, not some cosmic rarity, thus putting more pressure on the search for a mechanism to explain how they got there. Discounting primordial black holes, hypothesized to be left over after the Big Bang, the 3 main categories of black holes are stellar mass black holes, which have mass between 5 and 100 times the Sun, intermediate mass black holes, with masses between 100 and 10,000 times that of the Sun, and supermassive black holes, which have masses mentioned above. Stellar mass black holes form when the most massive stars, with between 30 and 130 solar masses, run out of fuel for nuclear fusion and can no longer support themselves against their own gravity. As the outer layers of these stars are blown away in huge supernova explosions, the cores collapse to create stellar mass black holes, regions of space with a point of infinite density called a singularity at its center, and an outer boundary called the event horizon, where the force of gravity is so great not even light can escape it. supermassive black holes must form in a different way from stellar mass black holes, as it is impossible for a star to be large enough to have the initial starting mass to shed mass as it evolves through the events like the supernova that accompanies the gravitational collapse of the star, but still leave behind a core massive enough to become a supermassive black hole. For many years, astronomers have believed that supermassive black holes could start their lives as seed black holes that are much smaller, growing by first feeding on material and then merging with other black holes when the galaxies they reside in collide, something that also provides these budding supermassive black holes with gas and dust to feed on. The growth of stellar mass black hole seeds could happen when these cosmic seeds find themselves surrounded by vast amounts of matter and greedily feast on these material to rapidly grow into supermassive black holes. That process should be stunted, however, by something called the Eddington limit. The luminosity and brightness of a feeding black hole is proportional to the rate at which they are gathering mass. The faster a black hole consumes matter, the faster it grows. And the faster it grows, the more electromagnetic radiation is blasted out by its surroundings. But if the electromagnetic radiation emitted from around a black hole in the form of jets is intense enough, it physically pushes material away. This means the faster a black hole eats, the more likely it is to have its food supply interrupted and pushed away, thus halting that growth. The Eddington limit means that it should take black holes billions of years to accrete enough matter to reach supermassive black hole status. Regan is part of a team of researchers that investigated something called the super-Eddington accretion, which could account for the rapid growth of supermassive black holes in the early universe. This wouldn't, he explained, be anything particularly special, just a more rapid version of normal black hole feeding. This would lead to rapid episodes of feeding, with material pushed away by jets, halting feeding and thus cutting off the jets. This then allows the material to fall back to the black hole, thus triggering another bout of frenzied feasting. Regan and colleagues found this explanation unsatisfactory, however. He said, if you average this feeding cycle over time, it is actually less than the Eddington rate. It might be okay for 1 or 2 cycles, but overall, over time, it's not great because it just can't, and it doesn't go continuously. So we didn't find that this was a great mechanism to really explain supermassive black hole growth, he said. According to Regan, another possibility that he could explain the rapid growth of supermassive black holes is the idea that the seed black hole from which they grow is massive in size. Massive black hole seeds would still have to get into these dense environments, but at least they would have a head start on smaller seeds. Going back to the 6-foot infant analogy, Regan explains that the growth of this child is even tougher to explain if it was born with the length of an average infant. But if this child was born and it was already 3 feet long, its transformation to a 6-foot tall toddler isn't quite tough to explain after all. The problem with investigating this is, unlike toddlers, black holes lack any characteristics beyond their mass, angular momentum, which is spin, and their electric charge. Scientists call this the no-hair theorem, and it means that black holes are deceptively simple and don't carry information about their histories or evolution. Basu added that observing the feeding process that is bulking up black holes in the early universe hasn't been possible as it has been happening so far away from us. But detecting supermassive black hole feeding may be possible in the future. The hypothetical supermassive stars in the early universe would be extremely luminous, perhaps 10 billion times as bright as our Sun. It's possible that the JWST or Euclid could detect such objects if they are present as late as a few 100 million years after the Big Bang, Basu reported. Despite these issues, Regan is confident that by investigating black holes in the early universe and by potentially discovering heavy seeds, scientists will soon be able to build a supermassive black hole growth picture. In particular, he pointed to the launch of the Laser Interferometer Space-Based Antenna, or LISA, a space-based gravitational wave detector that will help scientists better constrain the demographics of black holes in the early universe. According to Regan, quote, "We made a huge amount of progress in the last 10 years, huge, and we will continue to make massive progress over the next decade as well. Extrapolating out from these demographics will give us a very, very good handle on the number of mergers happening in the distant universe involving black holes in exactly the mass range we need, with masses around 100,000 times that of the Sun. I think it's very probable we will have solved this problem in the next 5 to 10 years, end quote, he said.
Black holes are perhaps the most nightmarishly fascinating features of our universe. Like long, dark tunnels to nowhere or giant garbage disposals, these mysterious fixtures in space exert a gravitational pull so gripping that nothing close by, not even light, can escape from being swallowed. What goes in never comes out. For this reason, black holes are invisible to the eye, as lightless as the empty, dark space surrounding them. Scientists know they exist not because they can see an actual hole, but because a black hole's tremendous gravitational clench affects the orbits of nearby stars and gas. Another clue is the detectable radiation emitted as gas that's being sucked in is superheated. In fact, these strong X-ray emissions led to the discovery of the first black hole, Cygnus X1, in the constellation Cygnus in 1964. If all this sounds like science fiction, watch on. It's only the tip of the cosmic iceberg. As scientists are discovering, black holes are even stranger than science fiction. Believe it or not, some scientists and researchers believe that our entire universe is within a black hole. Tales say if we were to somehow breach the event horizon of a black hole and survive the journey into its interior, we could access new and unimaginable realities, dimensions, and truths beyond the ken of our myopic ape senses. We might even come across Matthew McConaughey in a 4D library from 2014's Interstellar. It sounds fanciful, even ridiculous. But in some ways, it's not only plausible, but solves a lot of problems with physics. So what if we, and our entire universe, are inside a black hole? What if the edge of the cosmos that we can never reach is actually the event horizon of a black hole we could never breach? Join us as we dig into details of the latest theory that the Big Bang could be wrong, and we might have been living inside a black hole all this time. Many people have likely wondered, if the Big Bang started everything, what existed before the Big Bang? This question is practically identical to its theological version. If God made everything, what made God? Some suggest that we just have to accept that we'll never understand the answers to such questions. After all, even the James Webb Space Telescope, the most powerful telescope in history, can see all the way to 100 million years after the Big Bang, but it can't pierce the first moments of existence. We know that the Big Bang happened about 13.7 billion years ago. By 10 to the power of negative 36 seconds after the Big Bang, or 1/1,000,000,000 of a trillionth of a trillionth of a second, the universe underwent an incredible growth spurt. During this burst of expansion, which is known as inflation, the universe grew exponentially and doubled in size at least 90 times. What happened immediately after the explosions is called the Planck era, the earliest known period of time. According to the theories of physics, 1 second after the Big Bang, the heat of the universe caused atoms to collide with enough force to create a 10 billion degree soup of neutrons, protons, electrons, positrons, photons, and neutrinos. Essentially, cosmic inflations created a soup of subatomic particle plasma. It appears that this is what gave rise to dark matter, and likely the phase in which matter gains superiority over antimatter. Within the first 300 seconds of the existence of the universe, the elements hydrogen, helium, and some lithium form from the protons and neutrons. This process is called nucleosynthesis and is a theory that accurately predicts the abundances of elements and isotopes found in the early samples of the universe, like some of oldest stars. This verification is a strong indication that our model of the universe is accurate. 300,000 years later, when the nearly uniform soup cooled, atoms formed other nuclei. Photons ceased to scatter through space, turning the prior opaque universe into one with visible light. Those same photons, the actual afterglow of the Big Bang known as cosmic background radiation, can still be observed today. About 1 million years after the Big Bang, we enter a period called the Dark Ages, which are known as the final frontier of cosmology. Little is known about this period, except that it was the period before the first stars were born. The Dark Ages are thought to have lasted about 100 million years. Then, 10 billion years after the Big Bang, dark energy, a mysterious force, starts to accelerate. After that, 13.8 billion years after the Big Bang, we reach our time today. As far as we can tell, this is an accurate portrait of our early universe, but the Big Bang picture is incomplete. A piece of the puzzle is missing, and this part is the earliest moments of the universe. That's a pretty big part. What was before the Big Bang? Some researchers postulate that the universe existed as a single, infinitely dense point called a singularity. That singularity ruptured and hasn't stopped expanding since. This is basically the opposite of a black hole. A black hole is also an infinitely dense point in space-time. Rather than spew everything out, though, it draws everything in. Could there be a connection there? Could the formation of a black hole equal the ignition of a new universe inside it? At this point, some readers might raise their hand and say, yeah, but black holes aren't the size of the universe. True enough. A tiny black hole like XTEJ1650500 has an event horizon, an outer rim, of 15 miles across. The biggest black hole in existence, the mind-splittingly gargantuan TON 618, has an event horizon of 262 billion miles across, or 43 times the diameter of our solar system. As absurdly big as that is, the entire universe is about 23 trillion light-years across. Even the part we can only see, 1/250th of the entire cosmos, houses 2 trillion galaxies. How could all that be inside a black hole? First off, remember that space is full of lots of just that, space, more than matter. But more importantly, remember that all black holes are points. The size of a black hole's event horizon depends on the black hole's mass. More mass equals bigger radius. We can reliably calculate that radius, the Schwarzschild radius, based on the equation written by German physicist Karl Schwarzschild. And insanely enough, if you gathered all the mass of our universe into a single bundle and plugged it into that equation, you'd get a radius that equals exactly the amount of the universe we can see. So, how about the edge of the universe? Is it possible to fly up to the edge of the cosmos and peer out of a one-way black hole mirror and into the universe that our universe nests within? Sadly, no. The universe is expanding so quickly that we could never reach the edge, but more importantly, there is no edge. Because of the open curvature of space-time, our universe is most likely shaped like a donut. Keep going, and you'd loop around to the same spot. And just like how you can't reach the edge of the universe, it's impossible to reach the center of a black hole. But doesn't a black hole suck up everything? Well, yes, but none of what it sucks up reaches its center intact. Objects caught in a black hole's gravity are drawn to a black hole's center at speeds approaching but not quite the speed of light. As Einstein stipulated through his theory of special relativity, an acclaimed E equals mc squared equation, time stops for objects moving at the speed of light. An object caught by a black hole won't live forever, though. Via a process dubbed spaghettification, objects within a black hole's accretion disk, the distorted space-time shape surrounding its singularity, are molecularly shredded while stuck at near zero time. So, if our universe exists within a black hole that exists within another universe, does that mean that reality is composed of a nested set of universes containing black holes, etc.? As wild as that sounds, yes. If it's true that each black hole contains its own distinct universe, then the true shape of the multiverse is something like a tree that keeps splintering into branches that split into further branches. Quotes physicist Nikodem Poplawski of the University of New Haven, each black hole represents a one-way door. A trip into a black hole would be a one-way trip that would rock the fundaments of human knowledge, but none of that knowledge could ever be communicated to anyone else. If this is true, then we still run across our original "what caused the first universe" question, or "what made God?" There are no answers for this. That being said, the black hole universe theory does help us solve a couple of other issues with physics. Namely, it might help explain dark energy. Dark energy is the unknown property that's fueling the expansion of the universe. No one knows what it really is, or why the universe not only continues to expand, but expands at an accelerated rate. So what if dark energy is caused by matter from outside of our black hole universe getting drawn into the black hole? The matter from outside becomes energy inside and fuels our expansion. This also might help explain the early, rapid inflation of the universe following the Big Bang. However, it's worth note that even though the black hole universe theory answers some questions, it raises others. Theory doesn't explain why our universe's initial inflation slowed down. We also don't know how matter from the outside becomes energy inside. Plus, we already mentioned the "what caused the initial universe" problem. But assuming we can resolve all these issues, it's unlikely we'd ever surmount a final, ultimate roadblock. As Big Think outlines, how could we begin to test this all? How could we check to see if we're inside a black hole? We can't approach the universe's edge because there isn't one. If objects entering our universe are spaghettified along the way, we can't exactly chat with an explorer on a one-way trip from our parent universe. Ultimately, we've got two lines of inquiry to investigate: cosmic microwave background radiation and Hawking radiation. The cosmic microwave background is a palette of evenly distributed, extremely cool cosmic energy left over from the Big Bang. Scientists like Roger Penrose have pointed to cosmic microwave background to say that it contains evidence of a universe that existed before the Big Bang, but he hasn't produced a lot of hard evidence. Hawking radiation is energy lost by black holes over a long period of time. Would we be able to track such a loss in our own cosmos as energy spills out of it? If not, we might have to accept that not every direct question can find a direct answer. The trail can simply grow cold or disappear. At that point, the most interesting question of all arises: what do you do next? Either way, the study of black holes continues to provide valuable insights into the nature of the universe, challenging our understanding of fundamental concepts in physics. Their existence questions the nature of space, time, and matter itself. Future observations, such as detecting gravitational waves from colliding black holes, promise to further unravel the mysteries of these enigmatic cosmic entities. As we continue to probe the depths of the universe, black holes stand as testaments to the complexity and majesty of the cosmos. They embody the eternal quest for knowledge and the human spirit's insatiable curiosity. In other words, black holes are like the ultimate A-listers of the universe, and scientists are the paparazzi trying to snap a picture of them. But it's no easy task. There are many obstacles they face in understanding these elusive celebs, including limited observations. Black holes are notorious for keeping a low profile, emitting no light or radiation. Scientists need to use indirect methods, like observing the behavior of nearby stars and gas, to figure out if a black hole is lurking in the shadows. Difficulty in detection. Even with indirect observations, finding black holes is like a game of Where's Waldo in space. They can be tiny, distant, and hard to spot among the stars. Plus, the tools used to locate them need to be super sharp, theoretical models and simulations. Scientists also turn to their imagination to study black holes, using complicated models and simulations to figure out how they work. But these models require a ton of computing power and are always a work in progress. Despite these challenges, scientists are not giving up on their pursuit of the ultimate cosmic superstar. With the help of advanced technologies and global collaborations, we are making significant progress in understanding these enigmatic entities. As we gather more information and observations, we'll unlock even more secrets about the universe's most mysterious objects. In the meantime, let's take a quick look at some of the most astounding characteristics and theoretical possibilities regarding these cosmic oddities. Black holes might have hair. In the 1960s, physicist John Wheeler suggested that black holes have no hair, meaning that each particular cosmic object could only be distinguished from its brethren by its spin, angular momentum, and mass. Any other differentiating information about a black hole is considered hair, and is thought to disappear behind a black hole's impenetrable event horizon, a boundary around the black hole beyond which nothing, including light, can escape. Cut to 2016, when famed physicist Stephen Hawking proposed that black holes actually sport an opulent hairdo made of ghostly zero-energy particles, and that this hirsute agglomeration contains information about material the black hole has consumed. This hypothesis has not been proven, but could help solve a long-standing paradox about what happens to gas and dust that has fallen into a black hole's maw. Black holes produce fountains. Nothing is supposed to be able to escape a black hole's powerful gravitational grip, but that only applies to material that has gotten extremely close to the hole's edge. Many black holes are, in fact, surrounded by streams of gas and dust, which circle around the hole like water going down a drain. Friction in this material generates heat, which creates churning, storm-like structures in the gas and dust. Recent observations suggest that this motion also produces arcing rings that surround inner columns of matter, which shoot straight into the air, strongly resembling fountains. Black holes can evaporate. Quantum mechanics provides another way for particles to escape a black hole. According to theory, pairs of subatomic particles are constantly blinking in and out of existence around a black hole's event horizon. Every so often, the configuration is aligned in just the right way to cause one of the partners to fall into the black hole. The particle's identical associate is then propelled away at extremely high speed, robbing the black hole of a tiny bit of energy. This produces what's known as Hawking radiation, after Stephen Hawking, who discovered the phenomenon. Because energy equals mass, this process actually can cause a black hole to shrink and eventually evaporate away over long periods of time. Black holes may be surrounded by a wall of fire. One of the problems with Hawking radiation is that it causes conundrums for physicists. The subatomic particles produced by this radiation are entangled, meaning that what happens to one is immediately felt by the other. So what does the partner that didn't fall into the black hole feel as its associate gets crushed into an infinitely dense point? Nobody knows. One theory holds that the black hole severs the particle's entanglement, an outcome that, according to the laws of quantum mechanics, would produce an insane amount of energy. That, in turn, would mean that all black holes are surrounded by roiling walls of fire. Black hole might scramble information, or not. It's hard to square black holes' crushing mass with the laws of quantum mechanics, which hold that information about particles can never be destroyed. But material that slips beyond a black hole's edge should become forever lost to the universe. This conundrum is known as the black hole information paradox. A resolution has eluded scientists to date. Recent research suggests that information that gets scrambled within a black hole could be passed to the outgoing particle partners in Hawking radiation. However, no definitive answer to this paradox has been found. Black holes could be dark matter. Shortly after the Big Bang, the universe should have produced a multitude of tiny black holes. Because these features would be massive objects that give off no light, some physicists have conjectured that these primordial black holes could account for dark matter, that mysterious material that the vast majority of matter in the cosmos is made of. But the idea is controversial given that data from the Laser Interferometer Gravitational Wave Observatory, or LIGO, has ruled out a universe filled with many minuscule black holes. Perhaps medium-sized black holes might still be lurking out there, though observations suggest they would only make up, at most, 1% to 10% of dark matter. Matter may travel to the future in a black hole. Black holes run into the problem of infinity. A black hole's mass is crushed to an infinitely dense point that's infinitely small in size. Physically, this doesn't make any sense, so researchers have searched for alternative frameworks to get a handle on black holes. One proposal is known as quantum loop gravity, which suggests that the fabric of space-time is curved very strongly near the center of the black hole. This would result in part of the hole extending into the future, meaning that matter getting sucked into it would time travel forward. So far, this mind-expanding idea remains theoretical. Scientists might have spotted black holes from another universe. One highly controversial observation suggests that our universe is a latecomer. Earlier universes might have existed before ours and would have contained black holes. Prominent Oxford University mathematical physicist Roger Penrose has argued that cosmic background radiation, an energetic relic from the Big Bang, contains imprints of these black holes from before time. Other scientists have argued that Penrose's data is nothing more than random noise, but the possibility remains intriguing. In short, black holes are like the Mick Jaggers of the universe, the ultimate cosmic rock stars. For centuries, scientists and the public alike have been captivated by these mysterious entities with their mind-bending, gravity-defying powers that continue to leave us in awe. But note that black holes are more than just celestial curiosities. They're the key to unlocking some of the universe's greatest mysteries. As we continue to develop new technologies and gather more observations, the future of black hole research is looking brighter than ever. Indeed, one of the supreme instruments is the James Webb Space Telescope. At the limits of today's observations, we've spotted black holes that are as massive as about 1 billion solar masses, a whopping 13.2 billion years ago, when the universe was merely the 5% of its present age. How did those early black holes get so massive so fast? It's not impossible, but it certainly is a challenge for our current theories to explain what we see. We would need, for example, a seed black hole of about 10,000 solar masses to form just 100 million years after the Big Bang, and it would then need to grow at the maximum rate that's physically allowed for the entire time just to get there. Either these black holes started off bigger than our theories expect, or they formed earlier than we realize, or they grow faster than we think they can. But that's where James Webb should shed a remarkable amount of light on these dark objects. With its infrared eyes and its position far away in space, James Webb is truly revealing the universe as we've only dreamed of seeing it, rife with tremendous advances and surprises. From on the Earth, we're severely limited by what sorts of light can be transmitted through the atmosphere. We can see optical light very well, but only small fractions of the ultraviolet and near-infrared portions of the spectrum. We can see almost no X-ray or gamma-ray light, and almost no mid-infrared, far-infrared, or microwave light before things become clear in the radio once again. That's the huge advantage of space. Not only do you remove the blurring effects of Earth's atmosphere, but some very important wavelengths of light are completely unobservable from the ground. Hubble provided a remarkable wealth of data, not only in optical wavelengths, but at near-infrared wavelengths as well. The reason Hubble looks like a tin can from up close is because we want it to be cold, to reflect as much of the light and heat that encounters it as possible. Infrared light is what we experience as heat, and we know that if things get hot enough, they'll glow in visible light, red, orange, yellow, or even white to blue if it's hot enough. Even if you can't see it glowing in visible light, objects like the Hubble Space Telescope do emit substantial amounts of light in the infrared. As a result, despite the reflective efforts that have been made with Hubble, it's only capable of observing out to about 2 microns in wavelength before thermal noise overwhelms the instruments. That's why James Webb is so remarkable in a number of ways, at least from an astronomer's point of view. Instead of being located in low Earth orbit, it's located at the L2 Lagrange point, 1.5 million kilometers from Earth. This way, it isn't constantly bathed in the direct infrared glow of Earth's heat. Instead of reflective material, there's a custom-built 5-layer sun shield that shields the telescope and instrument side from the sun, passively cooling things down to around $40 Kelvin, as opposed to 200 Kelvin for Hubble. And instead of a mirror configuration, an instrument suite optimized for observing at ultraviolet, optical, and shallow near-infrared wavelengths, James Webb was built to cover a little of the optical, all of the near-infrared, and much of the far-infrared over many wavelength ranges, plus the ability to perform spectroscopy on the entire near-infrared range of wavelengths. James Webb, armed with these capabilities, is capable of seeing galaxies that are too distant, too faint, and whose light has been stretched to too long a wavelength by the expanding universe to be seen by Hubble. And, because black holes accelerate the matter accreting onto them, supermassive black holes can often be seen in radio wavelengths, identifiable as quasars. With its infrared eyes, Webb will be able to pick out the host galaxies that house these quasars, allowing us to match them up at these great cosmic distances for the first time. If we want to understand how black holes grow in the young universe, there's no better tool than Webb for finding out. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.